Our entire universe was once smaller than a single atom. This is the breathtaking starting point of the Big Bang, the event that flung everything we know into existence. Yet the original theory was incomplete, missing a crucial piece of the puzzle. That piece is cosmic inflation, a concept so powerful it solves the universe's greatest riddles. We are about to journey through 25 of the most incredible discoveries that built our modern story of cosmic birth. You will learn exactly how we pieced together the history of everything, from a faint whisper of heat to the possibility of multiple universes. We will uncover why the cosmos looks the same in every direction and how ghostly quantum ripples built the galaxies. What single discovery about our origins still leaves you in awe? The universe was once too hot for light to travel. For nearly 400,000 years, a dense, searing fog of particles filled all of space, trapping light within it. Then, in an instant, everything changed. The cosmos cooled just enough for atoms to form, and for the first time, light broke free, flooding the universe in a brilliant flash. That primordial light is still here. It is the oldest story ever told, and it was discovered entirely by accident. In the mid-1960s, two radio astronomers named Arno Penzias and Robert Wilson were troubleshooting a strange, persistent hiss in their enormous horn antenna in Immerse. No matter where they pointed it, this faint microwave static remained. They scrubbed the antenna clean of pigeon droppings. They checked every wire, yet the noise would not go away. They had no idea they were listening to the faint, cooled echo of creation itself. This cosmic microwave background radiation is the afterglow of the Big Bang, a snapshot of the infant universe when it was only 380,000 years old. It permeates every cubic inch of the cosmos, a whisper of heat from a time long before stars or galaxies existed. Its discovery was the single strongest piece of evidence for the Big Bang model, effectively ending the debate over the steady-state theory which proposed a universe with no beginning. This uniform sea of radiation is our most direct line of sight back to the very beginning of everything. But this perfect snapshot held a deeper mystery, one that would only reveal itself decades later. That faint cosmic whisper was not the only echo of creation. While the cosmic microwave background gives us a picture of the universe hundreds of thousands of years after the beginning, an even earlier fingerprint was being forged in the universe's first few minutes. During this fleeting, violent period, the entire cosmos was a colossal nuclear fusion reactor. The temperatures and densities were so unimaginably high that the fundamental particles were smashing into one another, fusing into the very first atomic nuclei. This brief, explosive chapter is known as Big Bang nucleosynthesis, and it left behind a specific, predictable chemical signature. The theory predicted that this primordial cooking process would have produced a universe made of roughly 75% hydrogen and 25% helium, with only the tiniest trace of lithium. For decades, astronomers have measured the composition of the oldest stars and the most pristine, distant gas clouds in the universe, and what they find is a perfect match. Everywhere we look, the oldest material in the cosmos has that exact ratio of hydrogen to helium. This is not a coincidence. This specific abundance of the lightest elements could only have been cooked up in the unique, hot, dense conditions of the Big Bang's first moments. It acts as a second, independent pillar of evidence, a chemical fingerprint left over from the universe's infancy. Just as a detective uses forensic evidence to reconstruct a crime scene, cosmologists use this elemental fingerprint to confirm what the universe was like in its first 3 minutes. It tells us with stunning certainty that there was indeed a hot, dense beginning. But if the early universe was so hot and dense, Why does it look so remarkably smooth and uniform today? That faint, uniform glow of the cosmic microwave background presented cosmologists with a profound puzzle. Why would regions of the universe separated by vast distances, regions that could never have communicated with each other even at the speed of light, share the exact same temperature? This cosmic uniformity hinted at a deeper, more dynamic history, a story that actually began with a discovery made decades earlier in a California observatory. Edwin Hubble was meticulously studying the faint light from distant galaxies when he noticed something extraordinary. The light from almost every galaxy he observed was stretched, shifted toward the red end of the spectrum. This redshift meant that these galaxies were all racing away from us. But the truly revolutionary part was what happened when he compared their speeds to their distances. The farther away a galaxy was, the faster it was receding. This relationship, now known as Hubble's law, painted a stunning new picture of the cosmos. The universe itself was expanding. A simple way to visualize this is to think of the surface of a balloon being inflated. If you glue several small dots onto the balloon, you will see that as the balloon expands, every dot moves away from every other dot. A dot does not see itself as the center, it just sees all its neighbors fleeing. From any dot's perspective, the dots farther away appear to be moving faster than the ones nearby. This is precisely what Hubble discovered about our universe. We are not at the center of a grand exodus. Rather, space itself is stretching, carrying the galaxies along with it. This single observation fundamentally rewrote our cosmic story. The universe was not static and eternal as many had presumed. It was dynamic, evolving, and growing. And if you run this cosmic movie backward, you are forced to a single, inevitable conclusion. All that expanding matter and energy must have been compressed together in the distant past, into an unimaginably hot, dense, and singular point. That moment of infinite density is what we call the Big Bang. This expansion provided the crucial framework that made the Big Bang theory not just a possibility, but a logical necessity. Yet, the simple idea of an expanding universe from a single point created its own set of new and even more baffling mysteries. Hubble's discovery of an expanding universe solved one mystery but created another, far more perplexing one. This new puzzle centered on the very shape of the cosmos, a geometry of such perfect and unlikely balance it seemed to defy all odds. When cosmologists measured the large-scale geometry of the universe, they found it to be flat. This does not mean the universe is shaped like a sheet of paper. In cosmic terms, flat means that the fabric of space itself is not curved, that parallel laser beams will never converge or diverge as they travel across billions of light years. It describes a state of perfect equilibrium between the outward pull of expansion and the inward tug of gravity. The problem is that this flatness is an incredibly unstable condition. Think of trying to balance a sharp pencil perfectly on its point. The slightest nudge, the tiniest breath of air, and it will topple over. In the same way, any tiny deviation from perfect flatness in the early universe should have been wildly amplified by billions of years of cosmic expansion. If the density of the universe had been even a fraction higher at the beginning, gravity would have won, causing the entire cosmos to collapse back in on itself in a big crunch. If the density had been a fraction lower, the universe would have expanded so rapidly that matter would have flown apart too quickly to ever coalesce into galaxies, stars, or planets. For our universe to be as flat as we observe it today, its initial density at the moment of the Big Bang had to be fine-tuned to an astonishing, almost impossible precision. something like 1 part in a million trillion. This was the flatness problem, a glaring flaw in the standard Big Bang model. It suggested our existence hinged on a preposterously unlikely, razor's edge beginning. There had to be a mechanism, a physical process that forced the universe into this state of perfect balance, because pure chance seemed utterly implausible. This perfect uniformity of temperature presented a second, even deeper cosmic riddle. Why does the most distant cosmic microwave background we can see in one direction look exactly the same as the background we see in the opposite direction? According to the standard Big Bang timeline, these two regions are so far apart that light, or any form of information, has not had enough time since the beginning to travel between them. They exist beyond each other's cosmic horizon, forever isolated. Think of it like two people standing at opposite ends of a vast, dark plain, each holding a lantern. If they have never met, never communicated, and cannot even see each other's light, how is it possible that their lanterns are burning at the exact same temperature and brightness? This is the horizon problem. Without any way for these disconnected parts of the early universe to exchange heat and reach a common temperature, their perfect uniformity makes no sense. It is as if every room in a colossal, unbuilt mansion somehow agreed on a single, precise thermostat setting before the walls were even erected. This problem, combined with the impossible fine-tuning of the flatness problem, meant the classic Big Bang model was fundamentally incomplete. It described the universe's expansion beautifully, but it could not explain the universe's startlingly uniform and balanced initial conditions. Cosmologists realized they needed a new kind of physics, a dramatic addition to the story that could set the cosmic stage just right. The answer would come in the form of a breathtakingly brief and violent event that occurred in the very first fraction of a second of time. The solution arrived not from studying the vast cosmos, but from the bizarre rules governing the very small. In the late 1970s, a young physicist named Alan Guth was wrestling with problems in particle physics when he stumbled upon a mechanism that would revolutionize cosmology. He called it cosmic inflation. The theory proposed a breathtakingly brief and violent event in the universe's very first moments. In the tiniest fraction of a second, a strange, repulsive form of energy took command of the cosmos. This energy caused space itself to expand at an exponential, faster-than-light rate, doubling in size again and again in intervals so short they are almost meaningless to describe. A patch of space, smaller than a single proton, was stretched in an instant to a size larger than our entire observable universe today. This was not the steady, stately expansion Hubble discovered. This was a cosmic supernova of growth, a reset button for reality itself. And in one elegant stroke, it solved the two great puzzles of the Big Bang. First, it solved the flatness problem. Imagine the surface of a partially inflated balloon, covered in wrinkles and folds. Now blow that balloon up to the size of the Earth. From your perspective on its surface, any small patch of that balloon would appear perfectly flat and smooth. Inflation did exactly this to the fabric of the universe. By stretching that initial subatomic patch to such an enormous scale, any original curvature was ironed out, forcing the geometry of the cosmos into the precise flatness we observe. Second, it solved the horizon problem. Before inflation began, that tiny patch of universe was small enough for every part of it to be in intimate contact. Heat could flow freely, allowing the entire region to settle into a single, uniform temperature. Then, inflation acted like a cosmic zoom lens. It took that tiny, thermally equilibrated patch, and stretched it to become everything we can see. The entire observable universe, from one horizon to the other, was once a single, connected neighborhood that had time to agree on the thermostat before being blown up to cosmic proportions. Inflation provided the stunning answer. The universe looks the same everywhere because, in its first fleeting moment, it was the same everywhere. But that frantic period of inflation did more than just smooth and flatten the cosmos. It also provided the crucial ingredient for everything we see around us. The same quantum physics that governs the subatomic world tells us that empty space is not truly empty. At the tiniest scales, it is a seething, bubbling foam where particles and energy flicker in and out of existence. These are quantum fluctuations, momentary wrinkles in the fabric of reality itself. During the unimaginably dense first instant of inflation, these microscopic ripples were caught in the fabric of the inflattened field, the strange energy driving the expansion. As space stretched at a phenomenal rate, it did not stretch these quantum wrinkles smooth. Instead, it locked them in and magnified them, stretching those tiny quantum whispers into macroscopic ripples in the density of the universe. Think of a tiny, nearly invisible crease on the surface of a deflated balloon. When you inflate that balloon to the size of a building, that tiny crease becomes a vast, towering ridge. Inflation did exactly this, but on a cosmic scale. Those amplified quantum ripples became slight variations in density, some regions ever so slightly denser than others. And in a universe ruled by gravity, density is destiny. Over hundreds of millions of years, gravity began to pull matter toward these slightly denser spots. The more matter accumulated, the stronger the gravitational pull became, drawing in even more gas and dark matter. Those infinitesimal seeds, planted by quantum chance and blown up to cosmic proportions by inflation, grew into the first vast clouds of primordial gas, which then collapsed to form the first stars, the first galaxies, and eventually the cosmic web that structures our universe today. Without these quantum fluctuations, amplified by inflation, the universe would have remained a perfectly smooth, utterly dark, and profoundly boring sea of particles. There would be no clumps of matter, no gravitational anchors, no galaxies, no stars, no planets, and no us. The grand tapestry of the cosmos, with all its splendor and structure, began as nothing more than quantum static, a faint whisper from the void that inflation turned into a shout. Those quantum ripples, amplified to cosmic scales, left a permanent signature on the sky. For decades after its discovery, the cosmic microwave background appeared as a perfectly smooth sea of radiation, a uniform glow that confirmed the Big Bang but offered no clues to the origin of structure. The hunt was on for the faintest of imperfections in this primordial light, the telltale fingerprints of inflation's quantum seeds. This search required instruments of incredible sensitivity, launched above our murky atmosphere to get a crystal-clear view of the infant universe. The Cosmic Background Explorer, or COBE, satellite was the first to succeed. In 1992, its team announced a monumental discovery. They had found it. The background radiation was not perfectly uniform. Imprinted upon it were tiny variations in temperature, minuscule hotspots and cold spots, differing by only about 1 part in 100,000. It was like looking at a perfectly smooth ocean and finally seeing the gentle, rolling swells on its surface. This was the universe's baby picture, and it was speckled with the density seeds that would one day become galaxies. The COBE map was coarse, like a pixelated image, but it was enough to validate a core prediction of inflation. The journey to precision was just beginning. The Wilkinson Microwave Anisotropy Probe, WMAP, launched a decade later, provided a far sharper image. It transformed that pixelated map into a detailed cosmic portrait, clearly revealing the patterns of hot and cold that sprawl across the cosmos. Then came the Planck satellite, the most advanced observatory of its kind. Planck measured these tiny temperature differences with such breathtaking accuracy that it turned cosmology into a precise science. The specific statistical properties of these hot and cold spots, their sizes, and how they correlate with one another, match the predictions of inflationary theory with stunning fidelity. It is as if we found a fossilized bone, and its DNA perfectly matched a living animal we had only theorized. These anisotropies are more than just a picture, they are a cosmic barcode. By scanning this barcode, scientists can measure the fundamental ingredients of the universe with incredible accuracy. We now know the universe's age to within a fraction of a percent, precisely how much ordinary matter, and dark energy it contains, and the exact geometry of cosmic space. All of this information was encoded in those faint temperature variations, a message from the first moment of time, delivered across 14 billion years, and finally decoded. That cosmic barcode revealed far more than just the age of the universe. The Planck satellite's exquisitely precise map of the cosmic microwave background allowed scientists to perform a kind of cosmic accounting, adding up the total contents of the cosmos. The results were not just surprising, they were humbling. The ordinary matter that makes up everything we can see, from stars and planets to our own bodies, accounts for a mere 5% of the universe. The Big Bang did not primarily create a world of atoms and light. Instead, it gave birth to a cosmos dominated by two profound and invisible mysteries. The first is dark matter, making up about 27% of the universe. We cannot see it because it does not emit, absorb, or reflect light. Its presence is revealed only by its immense gravitational pull. We see its ghostly hand at work in the way galaxies spin. The stars at the outer edges of spiral galaxies orbit so quickly that they should be flung off into intergalactic space, like mud flying from a spinning wheel. The only thing holding them in is the gravity of an enormous, unseen mass, a vast spherical halo of dark matter that envelops each galaxy. This invisible scaffolding also governs the growth of cosmic structure. The slight density variations imprinted by inflation were primarily variations in dark matter. Its gravitational wells formed first, acting as traps that then collected the ordinary gas that would eventually spark into stars and galaxies. Without dark matter's gravitational backbone, the universe would have never woven itself into the grand cosmic web we see today. The second, and even more dominant component, is dark energy. This mysterious force makes up a staggering 68% of the cosmos. Its existence was inferred from a discovery about the modern universe that was as shocking as Hubble's original finding. In the late 1990s, two independent teams of astronomers were measuring the distances to extremely faraway supernovae, expecting to find that the expansion of the universe was slowing down due to the collective gravity of all matter. Instead, they found the opposite. The expansion is speeding up. Some repulsive force, which we now call dark energy, is overpowering gravity and pushing galaxies apart at an ever-increasing rate. This means the universe we see today is fundamentally different from the one that existed for billions of years. For most of cosmic history, gravity was the dominant force on the largest scales, gradually slowing the expansion. But around 5 billion years ago, dark energy took over. The ultimate fate of our cosmos is now a relentless, accelerating expansion into a cold, dark, and isolated future. So the story that began with a single, unified force of inflation appears to have come full circle. The universe was born in a burst of repulsive energy that stretched space, and it will end under the command of another form of repulsive energy that will stretch it into oblivion. The Big Bang created a world where 95% of reality is made of stuff we cannot see and do not understand. The quantum seeds planted during inflation did not simply grow into isolated islands. They gave rise to an architecture of breathtaking scale and complexity, a structure so vast it defies simple description. This is the cosmic web, the largest pattern in nature. If you could zoom out far enough to see the universe on its grandest scale, you would not see a random scattering of galaxies. Instead, you would witness a magnificent, interconnected network. Gigantic filaments of dark matter and galaxies stretch across the emptiness for hundreds of millions of light years, connecting at dense nodes where immense clusters of thousands of galaxies swarm together. Between these brilliant strands lie the cosmic voids, vast, nearly empty deserts of space that can span hundreds of millions of light years across. This is the large-scale structure of our universe, a spiderweb of matter woven across the cosmos. But how do we know this intricate pattern truly grew from those faint whispers in the cosmic microwave background? The proof comes from our ability to rerun the cosmic movie. Scientists input the precise initial conditions measured by the Planck satellite, the exact pattern of hot and cold spots from the infant universe, into some of the world's most powerful supercomputers. They program in the known laws of physics, primarily gravity, and the measured amounts of dark matter and dark energy. Then they press play. The simulation begins with a nearly smooth, expanding universe, dotted with the tiny density variations we observe in the CMB. As the virtual eons tick by, gravity goes to work. The slightly denser patches, dominated by dark matter, begin to pull in more and more material from their surroundings. Over billions of simulated years, a pattern emerges. Matter does not clump into a single mass, but instead flows along these emerging gravitational watersheds, collapsing into the vast, filamentary structure of the cosmic web. The stunning result is that these computer simulations, which start with the imprint from the Big Bang's afterglow, produce a universe that looks almost exactly like the one we observe through our telescopes today. The simulated distribution of galaxy clusters, the lengths of the filaments, and the sizes of the voids all match reality with remarkable precision. This is one of the most powerful validations of our entire cosmic story. It forges a direct and unbroken chain of cause and effect, linking the microscopic quantum ripples of the universe's first moment to the grand, galactic metropolises we see lighting up the darkness today. Those ghostly quantum ripples did more than just seed galaxies. They also set the early universe ringing like a colossal bell. In the seething plasma that filled the cosmos before the CMB was released, a fierce battle was underway. Dense pockets of matter, created by those initial quantum seeds, pulled inward with the force of gravity. But this inward pull was met with a powerful outward push from the intense radiation pressure of the trapped light. This titanic struggle between gravity and radiation pressure created powerful sound waves that raced through the primordial soup. These were not gentle waves. They were the loudest sounds in cosmic history, thundering across the universe at over half the speed of light. For nearly 400,000 years, these pressure waves, known as baryon acoustic oscillations, expanded outward in spherical shells from every single overdense region. Then, in an instant, it all stopped. When the universe cooled enough for atoms to form and light broke free, creating the cosmic microwave background, the music of the spheres suddenly fell silent. The radiation pressure vanished, and the waves froze in place, leaving behind a distinct fossilized imprint. Each of those racing sound waves left a spherical shell of matter at a very specific distance from its origin, like a cosmic fingerprint with a characteristic size. That distance, the farthest the sound wave could travel before the universe became transparent, became a permanent cosmic ruler. Today, we can see the ghost of that ruler in the way galaxies cluster together. When astronomers map the positions of millions of galaxies, they do not see a random scatter. They find that galaxies are slightly more likely to be separated by a specific distance, a scale of about 500 million light-years. This is the signature of those ancient sound waves. We see a subtle tendency for galaxies to form on the surfaces of these immense, fossilized shells. This baryon acoustic oscillation signal is one of the most powerful tools in cosmology. Because we know the exact physical size of this standard ruler from the physics of the early universe, we can use it to measure cosmic distances with phenomenal accuracy. By observing how this apparent size changes for galaxies at different distances, and thus from different eras, we can trace the expansion history of the universe across billions of years. This provides an entirely independent check on the story told by the cosmic microwave background and the supernova data. The incredible result is that all three lines of evidence, the CMB, the accelerating expansion from supernova, and the baryon acoustic oscillations, all point to the exact same cosmic recipe: a universe with dark energy, dark matter, and ordinary matter in precisely the amounts we have measured. The universe has provided us with a yardstick of its own making, and it confirms our strange and shadowy cosmos with unwavering consistency. This precise pattern of hot and cold spots is far more than a cosmic map. It is a detailed mathematical fingerprint. Cosmologists call this the primordial power spectrum. It is a graph that essentially counts the number of fluctuations of each possible size, revealing which wrinkles were most common in the infant universe. When scientists plotted this spectrum from the Planck satellite's exquisite data, they found a curve with a very specific shape. It is not flat. Instead, it has a gentle downward slope, a subtle tilt that tells a profound story. This tilt and the overall shape of the spectrum match the predictions of the simplest models of cosmic inflation almost perfectly. It is a stunning confirmation, like finding that a suspect's shoe perfectly matches a footprint left at the scene of the crime. But this fingerprint does more than just point a finger at inflation in general. It gives us a direct line of insight into the properties of the inflatoned field itself, that mysterious energy that powered the universe's explosive birth. The specific tilt of the spectrum tells us that the energy of the inflatoned field changed very, very slowly as it drove the expansion. Think of a ball rolling down a long, almost flat, and perfectly smooth hill. It loses energy gradually, not in a sudden drop. This slow roll is precisely what the power spectrum's tilt requires. A steeper drop would have produced a different pattern of fluctuations, one we simply do not see in the cosmos. Furthermore, the smoothness of the spectrum, the fact that there are no unexpected spikes or dips, suggests that the inflattened field's hill was remarkably featureless. Any bumps or valleys on that cosmic slope would have left sharp features in the power spectrum, like a recording of a skipping record. The data, however, shows a clean, gentle curve. So, from the faint temperature differences in the ancient sky, we can deduce the physics of a field that vanished in the first fraction of a second of time. We know it was a form of energy that dissipated slowly and smoothly, setting the stage for everything that followed. This is the power of modern cosmology, using the universe as a laboratory to probe its own most fleeting and fundamental moments. Those quantum fingerprints on the cosmic microwave background are not our only window into the early cosmos. Another, more ethereal record is written in the light of the most brilliant beacons in the universe. Billions of light years away, quasars act as cosmic lighthouses. These are the intensely luminous cores of young galaxies, powered by matter spiraling into supermassive black holes. Their light travels for aeons across the expanding universe before finally reaching our telescopes. But this journey is not through empty space. The vast expanses between galaxies are filled with a diffuse fog of neutral hydrogen gas, the leftover raw material from the Big Bang. As the quasar's brilliant white light passes through this primordial fog, a specific transformation occurs. The hydrogen atoms are tuned to absorb light at one very precise color, a wavelength known as the Lyman alpha line. Each time the light encounters a cloud of this hydrogen, a tiny bite is taken out of the quasar's spectrum at that specific color. But these clouds are not all at the same distance. They are scattered all along the immense path between us and the quasar. Because the universe is expanding, light from more distant clouds is stretched more, shifting the absorption line. The result is breathtaking. Instead of a single dark line, a quasar's spectrum reveals a veritable forest of thousands upon thousands of absorption lines, all at different redshifts. This is the Lyman alpha forest. Each line in this forest is a shadow cast by a single cloud of primordial hydrogen, and each cloud exists at a different moment in cosmic history. By decoding this forest, astronomers can do something extraordinary. They can create a core sample of the universe. Think of a geologist drilling into the ice of Antarctica. Each layer of ice represents a different era in Earth's climate history. In the same way, the light from a single quasar passes through hydrogen clouds from the recent universe all the way back to when the cosmos was only a few billion years old. The closer the lines are packed together in the spectrum, the denser the clouds were at that epoch. By analyzing the distribution and clustering of these lines, scientists can map the large-scale structure of the universe as it was billions of years ago. They can trace the faint tendrils of the cosmic web in its infancy, watching as gravity begins to pull matter into the filaments and nodes that will one day host galaxies. This provides a powerful, independent confirmation of our cosmic story. The pattern of this primordial gas, the way it clumps and clusters across vast distances, matches the predictions that start with the quantum seeds from inflation. The Lyman alpha forest shows us the invisible scaffolding of dark matter taking shape, with neutral hydrogen simply tracing its form. It is a direct glimpse into the era of structure formation, a living fossil that confirms the universe grew exactly as our models predicted, from a smooth beginning into the intricate cosmic web we see today. That brilliant flash of light from the cosmic microwave background did not last forever. The universe, having become transparent, then plunged into a profound darkness. For hundreds of millions of years, it was a vast, featureless sea of neutral hydrogen gas, a cosmic dark age where not a single star flickered, but the seeds of change were already planted. The quantum ripples from inflation had sculpted the dark matter into a hidden scaffold, and slowly, relentlessly, gravity began to pull the first clumps of gas into the deepest wells. This was the dawn of the first stars and galaxies, and their birth ignited a second great transformation of the cosmos. an event we call the epoch of reionization. When the very first stars switched on, they were not like the stars we see today. They were behemoths, hundreds of times more massive than our sun, and they burned with a ferocious, ultraviolet intensity. Their powerful radiation acted like a cosmic blowtorch, slamming into the surrounding fog of neutral hydrogen and blasting the electrons right off the atoms. This process, known as ionization, began to carve out growing bubbles of transparent, ionized plasma within the opaque neutral gas. One by one, then in growing numbers, these brilliant islands of light emerged, their ionization bubbles expanding and eventually merging. Over several 100 million years, this process swept across the entire universe, burning away the primordial hydrogen fog and returning the cosmos to a transparent state, this time for good. The cosmic dark ages were over, and the universe as we know it, filled with visible galaxies, had begun. But how can we possibly witness this ancient transition? The evidence is written in two very different kinds of light. The first clue comes from the cosmic microwave background itself. When the CMB light was first released, it scattered off the last of the free electrons. When the universe became neutral, that scattering stopped. But when reionization happened and all those atoms were ripped apart again, a new, much smaller population of free electrons was created. A tiny fraction of the CMB light, about 1%, scattered off these new electrons. This final scattering imprinted a specific, swirling pattern on the CMB, a subtle polarization that tells us precisely when this reionization occurred. Satellite maps from Planck show us that this epoch was well underway when the universe was only around 500 million years old. The second line of evidence comes from the other end of the timeline, from the Lyman alpha forest we see in quasar spectra. When we look at the most distant quasars, whose light comes to us from before reionization was complete, we see something dramatic. Their spectra show a nearly total blanketing absorption, a veritable wall of darkness at wavelengths shorter than Lyman alpha. This is the Gunn-Peterson trough, a telltale sign that the light is traveling through a universe still filled with neutral hydrogen, a fog so thick it blocks all distant ultraviolet light. For quasars a little closer, from a slightly later time, the fog has begun to clear, and the familiar forest of absorption lines reappears. This epoch of reionization is the crucial final link in our story. It marks the moment when the universe, forged in the Big Bang and structured by inflation's quantum seeds, finally woke up and turned on the lights. The very first structures, born from those microscopic ripples, changed the entire nature of the cosmos, ending its dark age and setting the stage for everything that was to come. This absence of magnetic monopoles was one of the most compelling reasons to invent inflation in the first place. To understand why, we must journey back to the universe's first split second, to a time of unimaginable energy when the fundamental forces of nature were not separate, but unified into a single, supreme force. Grand unified theories, which attempt to describe this era, predict a startling consequence of this unification. As the universe expanded and cooled, it underwent a dramatic phase transition, much like steam condensing into water. And just as freezing water can trap air bubbles to form cracks and fissures in ice, this cosmic freezing should have created bizarre topological defects. The most dramatic of these defects would be particles known as magnetic monopoles. Think of a monopole as the ultimate magnet, but with a crucial difference. Every magnet you have ever seen, from a simple refrigerator magnet to the Earth itself, has both a north and a south pole. A magnetic monopole, however, would be a solitary north pole without a south, or a south without a north, a fundamentally new kind of magnetic charge. According to the math, these particles would not just be oddities, they would be monstrous. Each one would be incredibly massive, perhaps as heavy as a bacterium, which for a single particle is an astronomical weight. And the theories predicted they should have been produced in staggering abundance, as common as protons in the early universe. If that were true, the mass of all these monopoles would have overwhelmed the cosmos, causing it to collapse back on itself almost immediately. Our universe would have been stillborn. Yet, when physicists began to search for them, they found nothing. No monopoles were detected in cosmic rays, in particle accelerators, or in ancient mica crystals that could have trapped them like fossils. The universe appeared to be completely clean of these predicted relics. Their absence was a glaring contradiction, a direct challenge to our understanding of physics. How could our theories be so right, yet so wrong? The answer, once again, was cosmic inflation. That furious stretching of space in the universe's first moment provided the perfect cosmic cleanup. Before inflation began, the grand unified theory was in effect, and a prodigious number of magnetic monopoles should have indeed formed, saturating the tiny primordial patch. But then, inflation switched on. It took that entire patch, brimming with monopoles, and expanded it to a size larger than our entire observable universe. This diluted the density of monopoles to such an incredible degree that the average distance between any two of them would now be far greater than the size of the cosmos we can see. Inflation did not destroy the monopoles. It simply pushed them so far away from each other that the chance of even one existing in our entire celestial neighborhood became vanishingly small. It swept them beyond our horizon, explaining their puzzling absence with a simple, elegant stroke. The universe is not missing its monopoles. Our observable universe is just one tiny, cleaned-up room in an impossibly vast mansion. This cosmic timeline, built from primordial sound waves and ancient light, gives us one of the most staggering numbers in all of science. The universe is 13.8 billion years old. This is not a rough estimate or a philosophical guess. It is a precise, derived parameter from our standard model of cosmology. Think of it like a detective determining the exact time of a crime by combining security camera footage, witness statements, and forensic evidence. Cosmologists do the same, using the cosmic microwave background as their primary witness. The specific pattern of hot and cold spots in the CMB, especially the apparent size of those spots, acts as a cosmic ruler. By measuring how this ruler appears in the sky, and combining it with our measurements of how fast the universe is expanding today, we can run the cosmic film in reverse with incredible accuracy, pinpointing the moment when everything began. This number, 13.8 billion years, is the result of that calculation. But what makes this figure so powerful is that it is cross-checked by entirely independent evidence. Astronomers can measure the ages of the oldest stars in our galaxy, ancient objects known as globular clusters. These are dense swarms of stars that formed when the Milky Way was just assembling itself. By studying the nuclear burning processes in these stars and applying the well-understood physics of stellar evolution, we can determine their ages with high confidence. The oldest of these stars are consistently dated to be just over 13 billion years old. This creates a beautiful and logical sequence. The universe itself is 13.8 billion years old, and the first stars in our own cosmic neighborhood ignited a few 100 million years later. The ages fit together perfectly. If our cosmological model gave an age of only 10 billion years, it would be a catastrophe because we can see stars that are clearly older. If it gave an age of 20 billion years, It would leave an unexplained void of time before the first stars switched on. The fact that the age derived from the Big Bang's afterglow agrees so perfectly with the ages of the oldest objects we can find is a profound validation. It tells us that our entire story, from the inflationary burst to the formation of galaxies, is not just a compelling narrative, but a chronologically consistent history of everything. This precise cosmic timeline now faces a startling challenge, one that has shaken the foundations of modern cosmology. We have two incredibly accurate ways to measure the universe's current expansion rate, known as the Hubble constant. One method uses the pristine conditions of the early universe, looking at the cosmic microwave background. The pattern of those ancient ripples, combined with our standard model, allows us to calculate how fast the universe should be expanding today. It is like calculating the final speed of a rocket by carefully examining its launch. The other method looks directly at the modern universe, using stellar explosions called supernova and other local probes to measure how fast galaxies are actually flying away from us right now. This is like using a radar gun to clock the rocket's current speed. Both methods are exquisitely precise. The problem is they do not agree. The early universe measurement gives one number, and the late universe measurement gives a consistently higher number. The universe appears to be expanding faster today than our best models, based on its baby picture, predict it should be. This discrepancy is known as the Hubble tension. It is not a small, negligible glitch. The gap is significant, and it has persisted and even grown as our measurements have become more and more refined. This is not a story of failure, but of a thrilling mystery. The Hubble tension is a potential clue, a crack in the elegant facade of our standard model of cosmology. It suggests that something is missing from our recipe for the universe. Perhaps dark energy is not a constant force, but an exotic energy that changes over time, growing stronger and pushing the expansion to accelerate faster than expected. Or maybe there are new, unknown types of neutrinos, ghostly particles that stream through the cosmos, subtly altering the rate of cosmic growth. This tension forces us to ask a profound question. Are we on the verge of discovering a fundamental new ingredient in our cosmic recipe? A piece of physics that operated in the shadows, unseen until now. The universe may be revealing its next great secret, not through a bold new signal, but through a persistent, whispering disagreement between its deepest past and its present reality. This persistent tension in the cosmos has sent scientists searching for an even more fundamental signal, a whisper from the very instant of creation itself. The ultimate smoking gun for cosmic inflation would be the direct detection of primordial gravitational waves. Just as a violent splash in a pond sends ripples across the water, the explosive jolt of inflation should have sent powerful ripples through the very fabric of spacetime. These are gravitational waves, but not like the ones we detect from colliding black holes today. These would be a background hum, a cosmic static generated when the universe was less than a trillionth of a second old. Their imprint would be the final and most dramatic signature on the cosmic microwave background. These waves would have a very specific effect on the ancient light. As they pass through the primordial plasma, they would have gently squeezed and stretched space in a particular way, imparting a swirling, curling pattern to the polarization of the CMB light. Scientists call this unique fingerprint B-mode polarization. Finding this subtle swirl in the sky would be like finding the fossilized footsteps of the inflattened field itself. The hunt for this signal is one of the most ambitious quests in modern science. At the most extreme locations on Earth, Like the cold, dry, and stable heights of the South Pole, teams have built incredibly sensitive telescopes with names like BICEP and Keck. These instruments stare at a single, pristine patch of sky for years, measuring the polarization of the CMB with a precision that is almost beyond belief. They are trying to measure a signal that is magnitudes fainter than the temperature variations we discussed earlier, a whisper within a whisper. The challenge is immense, as other effects, like dust within our own Milky Way galaxy, can create similar swirling patterns, mimicking the signal they so desperately seek. The story of this search has been a roller coaster. In 2014, the BICEP2 team announced a thrilling, tentative detection that sent waves of excitement through the scientific community. It appeared they had found the first evidence of these primordial gravitational waves, but further analysis, in collaboration with the Planck satellite data, revealed a sobering truth. The signal they detected was largely, if not entirely, caused by interstellar dust. It was a lesson in cosmic humility, a reminder of how difficult it is to listen to the first moment of time. Yet the search continues with even more powerful and refined instruments. Detecting this signal would do more than just confirm inflation. It would tell us the energy scale at which it happened, revealing the specific physics that powered the birth of our universe. It would open a direct window to a time before time, allowing us to witness the very mechanism that set everything in motion. The absence of a detection after an exhaustive search would be equally profound, forcing us to reconsider our most cherished theories of cosmic birth. This staggering mismatch between prediction and reality is known as the cosmological constant problem, and it represents the single greatest failure of theoretical physics. Our two most successful and rigorously tested theories, quantum mechanics and general relativity, come together to make a calculation about the energy of empty space. Quantum theory tells us that the vacuum is not truly empty, but a seething, bubbling foam where virtual particles pop in and out of existence. This quantum frenzy should endow every tiny patch of space with a colossal energy density, a powerful repulsive force. When you add up this energy across the entire universe, the number you get is so astronomically large it is almost meaningless. It should be 1 followed by 120 zeros. This is the predicted strength of the vacuum energy. Yet, our astronomical observations of dark energy, the force actually driving cosmic acceleration, measure its strength to be almost zero. Not just a little bit off, but 120 orders of magnitude too small. To grasp the absurdity of this discrepancy, imagine predicting that a single breath of air would be powerful enough to blow away every planet, star, and galaxy in the observable universe. But when you actually take that breath, you only manage to rustle a single leaf on a tree. The gap between the expected power and the observed effect is that vast, that incomprehensible. This is not a minor rounding error, it is a screaming paradox. It tells us with absolute certainty that our understanding of the vacuum, of nothingness itself, is fundamentally and catastrophically wrong. Something must be canceling out this vacuum energy with unimaginable precision, leaving behind only the faint whisper we call dark energy. Perhaps a new, undiscovered symmetry in nature acts as a cosmic accountant, perfectly balancing the books. Or maybe our entire concept of gravity needs a complete overhaul, a revolution that can only come from a theory of quantum gravity that unites the very large with the very small. The cosmological constant problem is the darkest, deepest shadow cast by the Big Bang, a silent reminder that for all we have discovered, The true nature of reality remains hidden in plain sight. The very mechanism that forged our universe may have also created an infinity of others. This is the staggering implication of the multiverse hypothesis, a concept that pushes cosmology to its absolute limits. The idea springs directly from the mathematics of eternal inflation. In this scenario, the repulsive energy that drove our cosmic inflation does not switch off everywhere at once. Instead, it ceases in localized patches, like bubbles forming in a vast, boiling pot of water. Each one of these bubbles is a separate Big Bang event, an entire universe nucleating out of the inflating background. Our entire cosmos, with its hundreds of billions of galaxies, would be just one bubble in this endless, frothing sea. The process is eternal, meaning new bubble universes are constantly being born, creating a multiverse of literally unimaginable scale. Within this endless proliferation, the consequences become even more profound. The fundamental laws of physics, the constants like the strength of gravity or the mass of an electron, which seem so finely tuned in our universe, may not be fundamental laws at all. They could be local bylaws, the accidental outcome of how our particular bubble formed and cooled. In another bubble universe, the inflattened field might have decayed differently, resulting in a cosmos where gravity is repulsive, atoms cannot hold together, or time itself flows backward. The multiverse suggests that every possible set of physical laws, every conceivable configuration of reality, is realized somewhere in this vast ensemble. This idea offers a controversial but compelling answer to the puzzle of our universe's apparent fine-tuning. Why does our cosmos have just the right rules to allow for stars, planets, and life? If there are an infinite number of universes, then it is no surprise that we find ourselves in one of the rare, hospitable ones. We are not a special creation, but simply a statistical inevitability in an endless cosmic lottery. While this remains a highly speculative frontier, untestable by any current experiment, it represents a logical endpoint for inflationary theory. It forces us to confront the ultimate nature of reality, blurring the line between fundamental physics and profound philosophy, and suggesting that our entire cosmic story may be just one paragraph in an infinite library of creation. This remarkable chain of cosmic events, from quantum ripples to galactic superclusters, leads us to a startling question about our own place in it all. The universe seems to have been calibrated with an almost unbelievable precision, fine-tuned in a way that allows for the existence of life. Consider the fundamental forces that hold reality together. The strength of gravity, the power of the nuclear force, the charge of an electron, these are not variable settings. They are fixed constants, the immutable rules of our cosmos. Yet, if any one of these rules had been even slightly different, the story of the universe would have ended almost before it began. If the force of gravity had been just a little stronger, the universe would have collapsed back on itself in a fiery big crunch long before stars could form. If it had been slightly weaker, matter would have flown apart too rapidly to ever coalesce into the first galaxies. The initial density fluctuations, those quantum seeds from inflation, were also set at a perfect volume. If they had been much stronger, matter would have clumped into monstrous black holes, with no delicate structures like stars or planets. If they had been much weaker, gravity would never have overcome the expansion, and the cosmos would have remained a forever dark and empty void. This fine-tuning extends to the very atoms that build our world. The nuclear forces are perfectly balanced to allow for the stable existence of carbon and oxygen, the essential elements for life as we know it. It appears we live in a universe that won a cosmic lottery, with every single dial set to an exact, life-permitting value. So how do we explain this incredible luck? One profound possibility is that cosmic inflation itself provides the context. If inflation is eternal, spawning an endless multiverse of bubble universes, then every possible combination of physical constants and initial conditions will be realized somewhere in that infinite ensemble. In most of those universes, the numbers are wrong and the cosmos remains sterile and dark. But in a rare, precious few like our own, the numbers line up just right. We are not the purpose of the universe, but we are a possible, and perhaps inevitable, outcome within a vast cosmic landscape where everything that can happen does happen. This idea transforms the question from why is our universe so special to why would we expect to find ourselves in anything other than a universe that can support us. The search for our origins has led us to a mirror, reflecting not just how the cosmos began, but how we came to be a part of its story. This relentless expansion, driven by dark energy, charts a cold and lonely destiny for our cosmos. We are living in the universe's brightest, most vibrant era, but this is only a temporary blaze against an unimaginably long and dark future. The ultimate fate predicted by our measurements is known as the heat death, or the Big Freeze. It is a forecast of profound isolation and decay, stretching across trillions upon trillions of years. As the acceleration continues, galaxies beyond our local group will begin to vanish. They will not explode or be destroyed. Instead, space between us and them will stretch so rapidly that their light can no longer bridge the growing chasm. One by one, they will redshift into invisibility, their light stretching into undetectable radio waves, and then into nothingness, until our entire observable universe contains only the merged wreckage of the Milky Way and Andromeda galaxies, adrift in an ocean of blackness. Within this isolated island, the fuel for new stars will eventually run out. The last stars will sputter and die, their embers cooling into black dwarfs. Even the most resilient structures, planets and asteroids, will be ripped apart by quantum tunneling over eons, their matter evaporating into radiation. Supermassive black holes, the last bastions of structure, will themselves slowly evaporate away via Hawking radiation over timelines that dwarf the current age of the universe. The final state is not a dramatic collapse, but a slow, irreversible fade. The universe will become a near-perfect vacuum, an utterly dark and cold void where the temperature approaches absolute zero. Occasional particles will flicker into existence, separated by distances so vast they will never interact. The cosmos will be a thin, uniform, and lifeless soup of diluted photons and subatomic particles, a state of maximum entropy where no energy can be harvested and no change can ever occur again. This is the final, chilling conclusion of the story that began with a hot, dense bang. The same initial conditions that seeded galaxies with quantum ripples also encoded this desolate end, a future where the universe's own accelerating growth becomes the engine of its eternal silence. But for all its explanatory power, cosmic inflation is not the only story on the table. Science thrives on competition, and other compelling theories offer radically different visions of our cosmic beginning. One of the most prominent alternatives is the cyclic model, which proposes a universe without a true beginning or end. In this picture, our Big Bang was not a singular creation event, but merely one turn in an endless cosmic cycle. Imagine our universe as an accordion, expanding for billions of years under the influence of dark energy, until all matter is diluted and galaxies are torn apart. Then, in a dramatic reversal, A mysterious force triggers a contraction, pulling everything back together in a big crunch. But instead of collapsing into a point, the universe rebounds in a new Big Bang, born from the ashes of the previous one. This cycle of expansion and contraction could repeat forever, with each new universe inheriting a smoothed-out geometry from the violent mixing of the previous collapse. This model can also explain the universe's uniformity and flatness, but it paints a very different philosophical picture, a cosmos that is eternal and cyclical, rather than having a single, definitive start. Another intriguing idea comes from string gas cosmology, rooted in the complex world of string theory. It suggests that before the Big Bang, the universe was a hot, dense gas of the fundamental vibrating strings that constitute all matter. In this primordial state, the strings were constantly colliding and interacting, naturally reaching a thermal equilibrium that explains the uniform temperature we see today. The transition to our expanding universe was not a violent inflationary burst, but a more gradual phase change as this string gas cooled. These theories challenge the inflationary paradigm on its own turf, attempting to solve the same puzzles without invoking a period of faster-than-light expansion. They remind us that the quest to understand our origins is a live and dynamic debate. While inflation currently has the strongest support from data, the final chapter on the universe's first moment is not yet written. The ultimate answer may lie in a theory we have not yet conceived, waiting for a future observation to point the way. To understand the universe at its birth, we must recreate its fiery conditions here on Earth. This is the monumental task of particle accelerators, machines that collide subatomic particles at velocities approaching the speed of light. The most powerful of these is the Large Hadron Collider, a 27-kilometer ring buried deep beneath the Swiss-French border. Inside its circular tunnel, physicists steer trillions of protons in opposite directions, accelerating them to unimaginable energies before smashing them together. These collisions are microscopic fireballs, recreating for a fleeting instant the intense heat and density that filled the entire cosmos just a fraction of a second after the Big Bang. Each collision is a tiny window back in time, allowing us to witness the fundamental particles and forces as they behaved at the dawn of everything. It was here that the Higgs boson was discovered, a particle that helps explain why other particles have mass, a cornerstone of our understanding of the early universe. But the quest is far from over. The same theories that suggest cosmic inflation also predict a new, hidden layer of reality, a concept known as supersymmetry. This elegant idea proposes that every known particle has a superpartner, a heavier shadow twin we have yet to detect. Finding just one of these superpartners would be a revolution. It could provide the identity of the mysterious inflatoned field itself, revealing the specific particle or force that powered the universe's explosive growth. Furthermore, the lightest of these supersymmetric particles is a prime candidate to solve another great cosmic mystery. It could be the very dark matter that forms the invisible backbone of galaxies. This is the profound connection particle accelerators provide. They bridge the vastest cosmic scales with the tiniest quantum realms. The physics that governs the first instance of the entire universe is encoded in the behavior of the smallest things in existence. By probing these fundamental interactions, we are not just studying particle physics, we are reading the original instruction manual for reality, searching for the clues that explain why our cosmos looks and behaves the way it does. The search for these shadow particles continues, pushing our engineering to its limits and our theories to their breaking point, all in the hope of catching a glimpse of the engine that started it all. Our cosmic story is far from complete, its next chapters waiting to be revealed by a new generation of eyes on the sky. These are not mere upgrades, but revolutionary instruments designed to probe the very limits of our knowledge. The James Webb Space Telescope, already peering deeper into the infrared than ever before, acts as a time machine to the cosmic dawn. It is capturing the faint glimmer of the very first stars and galaxies as they ignited, watching in real time as they blow away the primordial hydrogen fog during the epoch of reionization. Each ancient galaxy it finds is a data point in the story of how the invisible scaffolding of dark matter gathered the first brilliant structures out of the darkness. Meanwhile, here on Earth, the Simons Observatory is rising from the high Chilean desert. This suite of ultra-sensitive telescopes will map the cosmic microwave background with a resolution and precision that makes previous efforts seem blurry. It will scan for the subtle patterns of primordial gravitational waves with such power that it could finally detect the swirling B-mode polarization, the definitive whisper from inflation itself, or rule out entire classes of inflationary models. And looking to the near future, the Lightbird satellite will launch to observe the entire sky from the quiet vantage of space. Its sole mission is to hunt for that same inflationary signal, but with a focus and sensitivity free from the interference of our atmosphere. Together, these observatories form a trifecta of discovery. They will cross-examine the universe's earliest light, test the inflationary paradigm with relentless precision, and trace the formation of the very first structures. The answers they find may resolve the Hubble tension, unveil the nature of dark matter, or perhaps reveal something entirely unforeseen, something that will force us to rewrite our cosmic story once again. The greatest discoveries about our origins are likely still ahead, waiting for the right tool to bring them into focus. From the faint hiss of the cosmic microwave background to the ghostly scaffolding of dark matter, these 25 discoveries form an unbroken chain of evidence, a story of cosmic birth and evolution more incredible than any myth. We have journeyed from a singularity smaller than an atom to a multiverse of infinite potential, tracing how quantum whispers were stretched into galaxies and how the universe's own accelerating death is written into its first moments. This grand narrative is not the work of a single genius, but the collective achievement of thousands of curious minds over many decades, each one adding a vital piece to the puzzle. Their telescopes, satellites, and simulations have woven a tapestry of understanding that connects the first trillionth of a second to the present day. And in this vast, dynamic, and ever-expanding cosmos, our world is a tiny, fragile speck, yet it is a place from which we can look back and comprehend the very origins of space and time. We are the universe awakening to itself. So tell us, which of these discoveries left you most in awe? Was it the quantum seeds of all structure, the mysterious dominance of dark energy, or the breathtaking possibility of parallel universes? Share your thoughts in the comments below, and subscribe to continue exploring the deepest mysteries of the cosmos with us.